So I wanted to thank everyone for joining us for part 4 of the CUDA training series. My name is Tom Papa Theodore from the OLCF. Also on the call we have Helen He and Kevin Gott. They're the organizers from the NERSC LBL side. Today's topic is Fundamental CUDA Optimizations Part 2. And we're joined again by our friends from NVIDIA, so Bob Corvella, Robbie Searles, and Max Katz. Bob will start off by giving a presentation for about the first hour, and then Robbie will follow up by walking through the example program that we have for you today. And those slides and examples are available now for you on the event page if you'd like them. They're under the presentations and exercises tabs respectively. Right, and so if you have questions during the presentation, please ask them in the Zoom chat. And then Bob will periodically stop and answer them. And I guess that's all I have from my side. So I'll go ahead and pass things off to Bob. Welcome, Bob.
Thanks, Tom. Hi, everyone. This is Bob Corvella with NVIDIA Corporation. And I'd like to once again thank the folks at Oak Ridge and Berkeley Lab for providing all of the support and enabling to make this possible. This month, we are in our 4th installment of our CUDA training series, our CUDA programming training series. In the first 2 installments, we visited some of the basic concepts that are associated with, as I like to describe it, writing a syntactically correct program in CUDA that gives you the correct answer. That's, of course, the first task of any CUDA programmer. Until we're getting the right answer, we need not proceed further. However, immediately we are addressed with the issue of performance. Once we have code that is working correctly and gives us the right answer, we may ask questions like, is it performing as fast as it possibly could? Or, on the other end of the spectrum, why is it running so slow? In the last month's session and in this month's session, we are going to address basically the first 2 topics in terms of optimization. And if you were with us last month, you know that the topic that we focused on there was execution behavior. So we took a look at the architecture and the execution behavior of GPU code, and then from there, we observed some basic principles to achieve high performance. And the most important basic principle that we want to take away from last month's session was to expose a lot of parallelism. And if we translate that even more simply, we could say run a lot of threads. And we delved into that topic with a little bit more detail in last month's session. So that was our first CUDA optimization priority. And this month, we want to talk about our second CUDA optimization priority, which in a nutshell is to make efficient use of the memory subsystems. One point that I made last month, which I'd like to state again this month, is this idea of training for optimization is something that has a dual nature to it. In other words, we could simply write correct code and then immediately switch to an analysis-driven optimization process and tackle performance that way. However, the suggestion I have and the way this series is organized is to tackle certain high-priority essential concepts for optimization, for writing code that will run quickly, and actually build them into your DNA as a CUDA programmer so that when you write code, you can immediately identify correct patterns. Now, this doesn't address every possible optimization topic. It's just 2 out of many. But my suggestion is that these are the 2 most important ones to achieve performance. So that's the idea. Last month and this month, we want to give you 2 of the most important ideas to achieve high performance in your CUDA code. And roughly speaking, we're going to relegate most of the rest of the optimization concepts to a later session where we'll talk about analysis-driven optimization. So let's dive into looking at the memory subsystem. This month, our focus will be on global memory throughput and also efficient use of shared memory. So as I mentioned, this is the second of our 2 most important training concepts for basic optimization skill, being actually able to write code that runs fast without having to turn to the profiler. So we'll start with global memory. We'll start with global memory throughput. And once again, we want to start with an understanding, as we did last month, of some aspects of the machine behavior. And we're going to derive from those aspects of the machine behavior some important principles for arranging our accesses to global memory. So we're going to start with reviewing what the memory hierarchy of a GPU looks like. And we're starting hierarchically at the type of storage that is the closest to the processing activity, and we call this local storage. Each thread has its own logical local storage space, and the most important resource there is registers. Registers are high-speed memory storage within the GPU itself, and they are both the source and the destination of nearly all low-level machine instructions. So nearly all low-level machine instructions that do any sort of calculation, arithmetic, will take their input from registers and place their output in registers. And so we want, of course, this resource to be the fastest, and it is the fastest resource. Register usage is really managed by the compiler, so from time to time questions come up about register usage and can I manually assign things to registers, and could I do a better job of choosing which registers to store which data in and so forth. Generally, the answer to all that is no. You should write code the way you would as a C programmer or as a C++ programmer, and for the most part, you want to let the compiler manage that. And really, you have no exposed controls for explicit usage of registers. So even though registers are an important resource, they're mostly managed by the compiler. And at this level of instruction, we're really not going to be spending any attention trying to think about or optimize usage of registers. The next level in the memory hierarchy would be the shared memory and the L1. These are also both on-chip resources, so they're part of the GPU die itself. They don't exist off-chip. We already have a basic idea of what shared memory is. It's a local memory array that can be allocated explicitly by the programmer and used for temporary storage of data. And as we alluded to in the past, because it's on chip, it also happens to be a fast source of memory, a fast source of data. There is some programmable or configurable characteristic to this, so we won't spend much time on that, but it is something to be aware of, and it varies based on the GPU architecture, the characteristics of programmability. All GPUs will have a minimum of 48 kbytes of shared memory that can be used per thread block. Some GPUs give you the option to actually use more, and if you're going to use more than 48K, you will have to use specific methods to achieve that additional storage capacity, 64K per thread block, or not, in some cases, 96 kbytes per thread block. The other resource that we're talking about here is the L1 cache. That's what L1 means. And L1 cache is, again, not a user explicitly managed resource. It's mostly invisible to the programmer. But it is, like all other caches, it's designed to improve the performance by retaining recently used data in the hopes that it will be used again. And if it is, it can be retrieved from the L1 as opposed to going out to global memory or wherever that data was. Both of these are high throughput and relatively low latency resources because both of them physically are backed by resources that are on the GPU die itself. And so we'll have, typically for both the L1 cache and shared memory, we have aggregate throughputs that are much higher than what is available from global memory. As we move down the memory hierarchy, the next item that we'll hit, I'm going to have a diagram of this shortly, so hopefully that will help a little bit. But the next item that we'll hit in the memory hierarchy is the L2 cache. The L2 cache is similar to the L1 in that it is a cache, and it is designed to provide performance benefit for recently accessed data. There are some differences with the L2. The L2 is a device-wide resource, whereas the L1 is a per thread block resource, or a per SM resource is a more accurate way to state it. So for the L2, it's a device-wide resource, which means all data goes through the L2 before it gets to global memory. And so the L2 is a device-wide resource in that respect. When we get to the bottom of the hierarchy, and this is really going to be our first focus for this session, we are now talking about global memory. That's the most distant resource, if you will, from the processing activity on the GPU. And global memory is just the memory that we talked about when we did allocations like CUDA malloc, and it was the source or destination when we were doing operations like CUDA memcopy. So global memory is basically the first resource that gets used by any CUDA programmer to provide data to the GPU for computation. It's accessible by all threads, and of course it's also accessible by the host using API calls like CUDA memcopy. Compared to the other resources that we've talked about in this hierarchy, it has relatively high latency. We learned what the definition of latency was in the last session. It's the difference between when you ask for something and when you receive it. And so when you want to access data out of global memory, you make a request for that data, and it takes some period of time for the data actually to become available. In effect, when the data is available, it basically means that it's deposited in a register and therefore can be used by subsequent instructions. This difference in time between when you request the data and when it appears in a register is called the latency. And the latency for global memory access is typically on the order of hundreds of cycles, 100 or more cycles. This can vary by GPU architecture, and we're not going to focus on the specific number. We simply want to point out that it's relatively long. It's a relatively long latency, and if this latency becomes a problem, it will definitely be a performance limiter to our code. And so we understood from last session that the GPU is a latency hiding machine, and so one of our strategies, of course, to deal with any sort of latency in the GPU is to take advantage of the GPU latency hiding capabilities, namely to switch to other available work. Global memory does have relatively high throughput, but this relatively high characterization or comparison is with respect to other types of memory that might be in your computer architecture, like system memory. It's still the lowest level of throughput compared to other elements of the memory hierarchy on the GPU that we've talked about. However, that throughput number there, 900 gigabytes per second for Volta V100, is one of the distinguishing characteristics of GPUs when we compare it to other types of processors. And one of the reasons that people like to use GPUs is for that number right there. So depending on what you're comparing it to, other elements of the memory hierarchy on the GPU, it's relatively low throughput. However, when we compare it to other processor architectures, it's relatively high throughput. And that's indeed one of the advantages of the GPU and why people use GPUs for increasing the performance of their code. So this is a pictorial diagram of the memory hierarchy, and this actually shows you the host as well. All processors, or most processors that I'm familiar with anyway, have a defined memory hierarchy. They have a stack starting out with memory or memory resources that are closest to the point of execution and then moving more and more distant from that point. And typically what we observe in a memory hierarchy is the resources that are closest to the point of execution are the most limited in terms of size, but also the fastest. And as we move farther away, what we typically observe in the memory hierarchy is that the resources become more prevalent. There's more of them, the size is bigger, but they generally become slower, whether you're talking about latency or throughput. And that's true of the GPU as well. So on the right-hand side, we see the GPU memory hierarchy. The GPU is depicted, the GPU chip itself is depicted in blue. So that GPU chip itself, we know from our last session, has these things called multiprocessors or SMs. Each multiprocessor or SM has a complement of registers and shared memory. Each multiprocessor also has a complement of L1 cache, and the GPU die itself has a complement of L2 cache. We'll see another pictorial diagram that will make this distinction clear. And there are other types of caches on the GPU. We're not going to be talking about those during this session. However, you should be aware that as you become a more adept CUDA programmer, there are other types of caches on the GPU. They tend to have a specific or canonical purpose for which they're used. And as you become a more adept programmer, you may want to try and take advantage of some of those other caches. And we won't cover that in this session, but at the final end of this session, I'll just have a note that says, don't forget there are other caches. And making use of these additional caches can tactically give you additional performance for your code, but we won't be covering them in this session. The green resource on the right-hand side represents DRAM memory. This is now on the device. The device is the GPU board, and typically the DRAM memory for a GPU is not contained on the GPU die itself. It may be located in a multi-chip module, or it may be located as an entity that is on the GPU board itself and is connected to the GPU via traces on the board. Nevertheless, it's separate. It's not part of the GPU die, the DRAM that we use as the physical backing for global memory. And in fact, the physical backing for some other logical programming spaces or logical memory spaces is depicted here as well. I use the word local on the last couple slides without defining it too well, but that actually refers to a logical distinction of data or memory. Global also refers to a logical distinction of data or memory. And the GPU has other specific logical spaces, constant, texture, and some other spaces as well. We are mostly focused on the global space. We didn't think too much about the local space. Another logical space on in the GPU is shared memory. So those are some examples of logical spaces. And the logical spaces are physically backed by varying resources on the GPU. The shared memory is backed by a physical resource that's on the GPU die itself. And the local and global spaces are physically backed either by registers or by DRAM, in other words, off-chip GPU memory. And of course, we have the connection to the host, and the host has its memory hierarchy as well. That's not the focus for our treatment today, so we're not going to be spending much time thinking about host memory hierarchy. Really, the purpose of the host is just to transfer data, as we've depicted here, to the GPU. Another view of a single GPU could be like this. This is just more reinforcement of the same ideas. So a GPU, as we talked about in the last session, can be thought of as a collection of SMs. The SMs are like cookie cutter sections of logic, sections of the GPU die, and we put one or more of these down on a GPU die, and that's how we build our GPUs. When we have more SMs, we typically have a larger GPU, a more powerful GPU, and we have fewer SMs, we have a smaller, less powerful GPU. Each SM, as I mentioned, has some of our memory hierarchy in it. It has the registers, which are part of the physical backing for the local space, the logical local space. And it also contains L1 cache resources and shared memory resources. As depicted on this diagram, the L2 is a device-wide resource. So it is a separate physical entity from the SMs. It's actually a separate part of the GPU die, and each SM talks to the L2, and on the other side of the L2, thinking logically now, is global memory, or DRAM, or off-chip memory. Now, we want to drill into the idea, with that picture of the memory hierarchy in our mind, we want to drill into the idea of what is the impact, how do memory operations behave, and what are the implications for performance. So we're going to divide memory operations into two types, loads and stores, and we could further subdivide some of these types if you wanted to. For instance, we may, I'll briefly mention something called a non-caching load, but we're going to focus for our treatment of load operations for the most part for this session on what we call caching loads. A caching load in a nutshell just means that the caches are enabled for that activity or that transaction. This is the default behavior of the GPU in some degree. In other words, the L2 cache is pretty much always enabled. And so when we load data from, let's say, global memory, the load request doesn't necessarily immediately go to global memory. What it will happen is it will attempt to hit in L1. In other words, it will attempt to query the L1 cache to determine whether or not that data is already present in the L1 cache. Remember, the cache is a mechanism to increase processor performance by keeping a store of recently accessed data. So to hit in the L1 implies that whatever you're asking for was already asked for at least once. And in the case of the L1, it means it was already asked for at least once by some CUDA thread running on that SM, because the L1 is a per SM resource. So the activity sequence here is first we will attempt to hit in the L1, in other words, discover whether or not the data is in L1. If it is, the request will be serviced out of L1, and that's generally faster in terms of latency and throughput than the alternative. However, if the query to the L1 indicates that the data is not in the L1, then we will perform a similar operation with the L2. We will attempt to find out if the data is in the L2. Remember, the L2 is a device-wide resource, so the difference here now is that any thread in any SM on the device may have requested that data previously. If so, a copy of it may exist in the L2. At that point, any other thread that queries the L2 would be able to retrieve that data item from the L2 without having to go to global memory, go to DRAM. However, if we miss in the L1 and miss in the L2, then of course we're going to have to retrieve the data from global memory. And once again, that's the focus of this session, because that's really the starting point. All of your data initially will live in global memory, and the safe assumption is there are no copies of it in L1 or L2. So when your code begins to execute, that should be your thought process. The data's in global, and I really can't depend on any benefit from L1 and L2. And L1 and L2 are typically not explicitly user managed anyway. So you're not going to be coding specifically to take advantage of L1 or L2, at least not at this level of instruction. Okay, so we're going to tackle the problem that every code is going to run into, which is accessing data from global memory. When we're talking about caches, the load granularity is a 128-byte what's called line. A line is a subdivision of a cache. It's a unit of transaction. It's a unit of request and load and store. So I don't get to request or access a single byte. Instead, I have to determine whether or not the line has what I'm interested in. On the store operation, it's a little bit different. We're not actually looking for data. We have data, and we want to deposit it in the right place. The typical methodology for store is to invalidate that cache line in the L1. So when I'm storing data, it means the data's changed from what was previously available, previously would have been accessed, and therefore what I want to do is declare that the contents of that cache line in L1 are no longer valid. That's called invalidation of the L1, or invalidation of that line in the cache. And that indicates now that if a future request for that data goes to the L1, it will miss in the L1. The behavior, the typical behavior of L2 is a write-back behavior. What this means is that the data that's being written on the store operation will update the L2, and at some future date will be written out to global memory. There's a lot of nuances and complexity here, which I don't wish to delve into, because once again, the L1 and L2 are not things that we're going to be explicitly managing at this level of instruction, and it's not actually germane to the process of getting the data to begin with. It's not the focus for this session, but nevertheless, that's the typical behavior for L1 and L2. There is also something called a non-caching load, and in a nutshell, what a non-caching load is, it just modifies the previous description by saying, I always miss in the L1. So if I'm doing a load, it means that I don't bother checking the L1, I simply go to L2. And there may be some reasons why you might want to do this. We're not going to drill into those too heavily, but what you can think about is the process of inter-thread communication. If I have some threads running on a particular SM and some threads running on another SM, the L1 caches between those two SMs are not guaranteed to be coherent. They're not guaranteed to be identical carbon copies of each other at every point in the computation. If you need that behavior, for instance, if you want to write data from one thread and have it be visible to another thread, and that thread might be running in another SM, then one of the things you'll need to be aware of is the effect of the cache on this. You don't want that thread in the other SM to read its data out of its L1 because that L1 hasn't been updated. And so that would be an example of where you might typically want to use a non-caching load from a programming standpoint. Now, from a performance standpoint, as we'll see, and the reason that we're discussing this at all and exposing it during this session is that from a performance standpoint, there are some, let me call them corner cases, where explicitly choosing a non-caching load may actually give you better performance for a particular access pattern. We'll see more about what that means around the midpoint or towards the end of this presentation. Nevertheless, it's not really the focus of our treatment today, and so we'll simply note that there is the possibility to do a non-caching load. There are a few different ways to achieve that. One of them is a device-wide or a program-wide operation at compile time, and there are other ways to do it on a transaction-by-transaction basis as well. But it's not the focus of our session today. Getting into more details now. Again, we're going to take a look at the architecture. We're going to look at the architectural behavior so as to inform ourselves about what is necessary for optimal performance. So we're talking about a memory operation, and our focus initially will be on a load operation. A load operation is nothing more than a load instruction that is executed warp-wide. Okay? All memory operations, like every other instruction on the GPU, is executed warp-wide. An instruction does not get issued to a single thread. It gets issued to a warp of 32 threads. So memory operations are issued per warp. It doesn't mean that every single thread in the warp is doing exactly the same thing. They may be retrieving data from different places, but nevertheless, they're all doing a load operation. Therefore, each thread in the warp could be requesting a different memory address for that load operation, and in the typical case, we would have 32 threads with effectively 32 addresses, probably 32 different addresses. And we need to retrieve the data from all 32 of those addresses in order to satisfy that load operation for that warp. So what the memory controller does now, once the instruction's issued, the memory controller will take that pattern of addresses, those up to 32 addresses, and it will determine which lines or segments are needed. I've defined the word line for you. It's a subdivision of a cache. We can think of a segment as an equivalent subdivision of global memory. It turns out that with modern DRAM architectures, you don't get to request a single byte. What you get to request, in other words, the unit of transaction, is what's called a segment. Now, the definition of a segment may vary depending on your DRAM design, but in all CUDA GPU designs up till now, the definition of a segment is 32 bytes. So what you get to ask from DRAM is not a single byte or a float quantity or a word or anything like that. What you get to ask for or what you get to store is a segment. Either you get 32 bytes or you store 32 bytes. And so the memory controller, in order to determine what needs to be retrieved from memory, let's say retrieved from DRAM if we're talking about segments, will have to determine which segments those addresses fall into. That's a mapping operation. The memory controller knows how to do that. And it will retrieve the necessary segments from memory or the necessary lines from cache in order to satisfy the request. And once that request for the needed lines or segments is completed, then the data will be provided to the warp and complete that instruction, and that typically means that that data would be deposited in registers. So what we now want to do is consider what we've learned just now about this warp-wide issuing of a load instruction and see what is the implication of this activity of retrieving not a single byte, but lines or segments at a time. And how does that behavior affect performance? So we're going to consider several different cases. And the difference in these cases is effectively a difference in the pattern of addresses across the warp. And in each case, I will try to provide a line of C code that will hopefully guide your thinking. And so in this case, what we're considering is a load where the addresses from the warp are basically adjacent and sequential. We remember that a warp consists of 32 threads, and so you could imagine that there's effectively 32 arrows in this diagram, and the 32 arrows in the diagram each represent an address, the indication of the address from that thread. A line of C code that might produce this kind of pattern where each thread in the warp is accessing the next element in memory, if you want to think about it that way, is what I've depicted here on the left-hand side. In other words, int C equals A of IDX. What is IDX? IDX is that canonical, globally unique thread index that you've played with in the homework and that we've discussed in the last few sections. Int IDX equals thread IDX.x plus blockdim.x times block IDX.x. That creates a globally unique index across our thread array, and it means that every thread in the warp will have a sequential index associated with it. If thread 0 has an index of 32, then thread 1 will have an index of 33. and thread 2 will have an index of 34, and so on. If we use that sequential index across the warp to access an array or a vector in memory, then it means that each thread in the warp will be requesting an adjacent element in that vector or array. That's exactly what we're trying to suggest here, and that's exactly what we're depicting with this pattern of addresses and this pattern of arrows. And we could imagine any starting point, but we'll imagine a starting point for this index pattern where the addresses happen to fall within memory on a segment boundary. And in this case, we're depicting a 128-byte line or segment, but you could also imagine that if we were talking about memory, that this could be broken, this red area could be broken into 4 blocks. And you'll get a brief view of that later in this discussion. But since this is a caching load, there's the possibility to service this transaction out of the cache, and that may imply a 128-byte cache line. So the effect of this then is that in order to service this request across the warp, we have to provide the data associated with each address. And because of this particular pattern we've chosen, these items happen to fall into a single cache line, or we could imagine this as a single or the smallest number of segments. Furthermore, if the cache line is 128 bytes and we're requesting 4 bytes per thread, like an int or float quantity per thread, then we will use exactly 128 bytes in order to service this transaction. And we can get all 128 of those bytes by requesting a single cache line, or in the case of memory, 4 segments, the minimum number of segments. It means that every single byte that we requested is needed. No bytes are wasted. There's nothing extra that was requested that wasn't used by one thread in the warp. We would call that a bus utilization of 100%. Every byte that was requested was used. And we would refer to that as perfect coalescing, or ideal coalescing, or 100% coalescing. Now I'm introducing a new word, coalescing. What coalesce means in the general sense, English, is a grouping or a collection. You can imagine things that kind of stick together. They coalesce, a set of things that group together. Coalescing in the GPU means almost exactly that. What's happening is we initially have a set of 32 threads that supply 32 different addresses. And the memory controller has to decide what to do. In the process of deciding what to do, it coalesces or groups those addresses together based on which line or segment they fall in. And then instead of requesting 32 individual addresses, it requests a set of line or segments. This process of grouping addresses into lines and segments is called coalescing in the memory controller. And if we have perfect coalescing, it means exactly what I described, which is that all of the addresses can be satisfied with effectively the minimum number of lines or segments. No bytes are wasted. Every byte requested is used. Okay, let's consider some other cases. Here's a different addressing pattern, and I've basically put some silly code in there to try and suggest what this could look like. In other words, if I had a random number and the random number was constrained to be within a range of indices associated with a warp, like constrained to be between 32 and 63 or 0 and 31 or something like that. If I had the random grouping of indices across the warp, then my addresses would be sort of pointing in random places as I've depicted with the arrows on this diagram. But nevertheless, all of the addresses, because of the way I've concocted this code, all of the addresses fall within the same pattern, the same memory area, the same lines or segments. And as a result of that, there's actually no difference. We're retrieving the same data and we're simply swizzling that data. We're moving that data around as we deliver it to the threads in the warp that need that data. There's no difference in behavior for all current GPUs with this sort of a pattern. This is once again a 100% coalescing or ideal coalescing situation. Let's start to deviate now from the 100% or ideal case, and our first deviation will be to look at this example. In this case, we're doing something quite similar to the first case we looked at, except we're offsetting it. Instead of IDX, this particular pattern is IDX -2. So thread 0 in the warp, instead of requesting index 32 is requesting index 30. Thread 1 in the warp, instead of requesting index 33, is requesting 31, and so on. Now, those numbers, those indices are all adjacent, but they're offset from the previous example, and in fact, they would straddle a line or segment boundary. I've tried to define lines and segments for you. They're subdivisions of either the cache or memory, and those subdivisions are fixed. They are not movable. They're defined by the architecture, and you're either on one side or another side of a boundary. In the previous two examples, all of our addresses fell within the same boundary area, and therefore they were either serviced by one line from cache or the minimum number of segments if going to global memory. In this case, they straddle a boundary, and therefore the memory controller will coalesce these addresses into two separate groups. One that belongs to the first boundary area here that's depicted from 0 to 128 in memory addresses, and most of the threads will fall or coalesce into the second area, which is depicted from 128 to 256. Therefore, the memory controller will have to request two lines or multiple segments to service this request. If we're requesting two cache lines, that means the memory controller is going to have to retrieve 256 bytes. Remember, you don't get to ask for anything less than the minimum quantum, a line from a cache or a segment from memory. And as a result, even though I didn't need all 128 bytes in that first area, in that first cache line, I had to retrieve the entire cache line in order to access the 8 bytes that I did need. As a result of this, our efficiency drops. Our bus utilization now drops to 50%. We're requesting twice as much data as we actually need for this particular instruction executed by this particular warp. And so this looks kind of bad. If this were the dominant factor in our programming, in our code, in our program, this would suggest immediately a 50% reduction in performance if our code was memory bound, if our code was limited by its ability to retrieve data from memory. However, there's a silver lining to this case, and the silver lining is that that bar that we're talking about there can be thought of as the cache. It really doesn't matter if it's the L1 or L2 cache. Nevertheless, it can be thought of as the cache. Even if it's not the cache, even if our reads initially go to global memory, what happens is after this transaction, after this instruction is complete, all of the red area is now populated in one or more of the caches, at least in the L2 and maybe in the L1. As a result of this, what would happen if other warps came to read data? Well, if we think about a typical data access pattern and think about a typical activity might be working on a vector or a matrix of data. And one of our canonical examples that we looked at already was a vector add operation. And so a vector add operation might consist of vectors that are very long, many elements, and we're using a large number of threads to perform the addition. And those threads are broken into warps, and in this case we're looking at a particular warp that's retrieving a particular value from its A vector in order to begin this process, let's say, of vector addition. However, there are other warps that are doing exactly the same thing, except they have different addresses. In fact, we could think of a warp to the left of the one that we're depicting here, and we could think of a warp to the right of the one that we're depicting here. And if it's a long vector, we could imagine many warps to the right, extending a long way off the right side of this diagram. So let's consider now the behavior of the next warp to the right, compared to the one that we're depicting here that says addresses from a warp. We're now looking at one warp to the right of that. Well, that warp to the right of that is going to have a set of arrows that look just like the ones here, except they're shifted to the right. That second warp that we're considering to the right, when it issues its instruction to read from A, it will need not the first line that we're depicting here, but it will need the second line and the third line. Now, the third line is shown in green in this diagram. We can think of that as something that's not yet been retrieved. It's not existing in any cache. But the third warp will need that. The third warp will also need the rightmost segment or line here that's depicted in red. It will need two elements or 8 bytes from that segment. But that is already in the cache because of this warp's activity. Therefore, for that additional instruction performed by that additional warp, how many lines do we actually have to retrieve from memory? We only have to retrieve 1 because some of the data that we need is already in the cache. And you could repeat that in an imaginary sense, you could repeat that as far to the right as you want. And if it's a long vector, what you'd be observing is that on average, each warp needs to retrieve approximately 1 line, not 2. And so the silver lining here is that for an extended pattern like this, many warps that are accessing adjacent data except shifted or offset, in fact, the cache will fix the problem for us. And the cache will make it so that we are actually achieving something much closer to 100% bus utilization, at least from the standpoint of global memory. Okay, let's continue. Here's another type of access pattern we could imagine. In this case, every thread in the warp, in fact, every thread in the entire grid, but let's say every thread in the warp is retrieving the same location from memory, A of 40. That might be something that arises from time to time in your code. And in that case, what we're pointing out here is that that access pattern is okay. There's no problem. It can be serviced. It's totally valid. And it will take us approximately the same time to service as if I had retrieved the entire line, like I depicted in my very first example for caching loads. Okay, so we're going to pull in an entire line here. We're going to pull in 128 bytes, but we only need 4 bytes if we're loading an int quantity. It's okay. It works. You don't have to be afraid of it, but it's not particularly efficient in terms of its utilization of bytes. If you do this once or occasionally in your code, don't worry about it. This is a flexible programming machine. That's why you have the C++ language that you can write your CUDA code in, as opposed to be giving the straitjacket of some sort of vector language that you would have to program in. Okay, so we're giving you the flexibility, and the machine will give you the flexibility to do things like this. However, if your code is dominated by this pattern of activity, this type of behavior, then that's something to think about. And there may be ways to refactor your code so that you don't have this kind of pattern occurring over and over and over again. For example, there might be a reorganization of the data or a reorganization of the workflow distributed across your threads so that you could get to a situation where you're using all of the data requested in that line as opposed to 1 or 4 bytes. Nevertheless, it's okay. However, when considered on this basis, the transaction efficiency is quite low. This is probably the worst case pattern, and this will arise from time to time as well. In this case, I'm in a kind of a silly way, I'm depicting this as using a random number as my index into the array A. But you could imagine, there's a number of other ways. Of course, that's not typical for programming, right? That's not a typical algorithm that does something like that. But there are certain other patterns that tend to occur from time to time where we get scrambled patterns that are more or less unavoidable. A typical case where this will arrive is through indirect indexing. If I'm retrieving A, and the index that I use to retrieve A is another matrix, so B of IDX inside that brackets instead of the RAND function, and that B of IDX basically contains a set of scrambled indexes, then that's a very common indirect indexing pattern which can easily lead to this type of access pattern. And so what we're saying in this type of access pattern is that the addresses from each warp can more or less point anywhere in memory. And if they're truly scattered, what we'll imagine is that each address points to a particular line or segment and no other address in that warp does. That means that in the worst case, which is what I'm depicting here, every thread in the warp would require its own line or segment to be retrieved from global memory in order to satisfy its needs. That would once again put us into this worst case pattern where we're at 3% efficiency. We're requesting 128 bytes, but only using 4 per thread in this case. So this would be a worst case pattern, And this is something that occurs from time to time in typical programming, so it's something to be aware of. When you get into a random access pattern, which is what we're trying to depict here, or a indexed pattern where the underlying indices are basically scattered, those are that should immediately raise a flag in your head that says this is an area where performance may suffer, at least compared to what I might observe if I had coalesced behavior. So this will be our last, basically our last example. And what we're depicting here now is the way we're using this last pattern that we just depicted, and what we want to do is just point out briefly, again, we want to revisit this idea of a non-caching load. Remember I said the non-caching load basically bypasses the L1 cache. And in the process of bypassing the L1 cache, the minimum transaction size gets converted from 128 bytes to 32 bytes. Remember I said that memory segments are actually 32 bytes long. And as a result of that, if I don't have to fill an entire 128-byte L1 cache line, and I have a scattered pattern like this, in fact, I can retrieve individual segments from memory, which are 32 bytes long, and I improve my overall performance as a result, because I'm retrieving less wasted data. And in that case, I've multiplied my efficiency from 3% to 12%. Okay. Let's keep going. So, some guidelines. We're just about done with our treatment of global memory, and after this we'll shift to shared memory. We want to strive for perfect coalescing. Again, that doesn't mean that any time you have detected that you have uncoalesced behavior that it's immediately a crisis and that you must do something about it. That's not the thought process here. The thought process here is, as you're writing your code, if possible, make arrangements to provide for coalesced behavior. And if you have occasional instances that are not coalesced, that's probably okay. That might be a topic that you'd want to defer to your analysis-driven optimization, which comes later, to decide whether or not this is a significant performance limiter for your code. In other words, something that you should spend your precious brain power on. Okay? But what we want to do is provide you so that in the general case, for the bulk of your activities, if possible, you as a programmer know how to write code by inspection that will properly coalesce without requiring a profiler to tell you if you've done a good job or not. You may want to align the starting address, but this is really, as we talked about in that example where we had the shifted indices, this is really something that I would not bother with. That's why I have it in parentheses here. But the basic idea is that we want to warp to access within a contiguous region, if at all possible. Okay? Another characteristic of global memory optimization would be to make sure that a memory-bound code can achieve maximum performance. If you have a memory-bound code and you're making efficient use of the memory subsystem, if you want to achieve maximum performance, it implies that your code must saturate the memory bus. It must keep the memory bus as busy as possible. If you have done all three of those things, you have a memory-bound code, you're making efficient use of the memory subsystem, and you saturate the memory bus, then you have achieved the optimal behavior for that memory-bound code. Okay, that code will definitely run as fast as possible without some kind of refactoring or algorithm transformation, as fast as possible for that realization. And so in order to do that, we want to make sure that we have enough concurrent accesses to saturate the bus. And then having enough concurrent accesses gets us immediately back into the topic that we dealt with in the previous session. So once again, for a memory-bound code, you probably want to think about having lots of threads. And there are other ways to increase the memory demand on a per-thread basis. For example, processing several elements per thread, and there's ways to do that. Something called a vector load is a common strategy here to load additional data per thread, or you could just simply have a loop that loads additional data per thread. Okay, and lastly is that thing that I said that I would remind you of, which is to use all the caches. Again, we haven't focused on caches because the L1 and L2 are not explicitly user-managed. But there are other caches that are explicitly user-enabled or user-managed, and as you become a more adept programmer, when you're looking for that extra 10 or 20% performance boost, you may want to figure out how to use something called the constant cache or something called the read-only cache, but we're not going to address those topics in this session. You will use the L1 and L2 automatically in the process of writing ordinary CUDA code. Let's talk about shared memory now. Shared memory is different. First of all, it's not backed by off-chip DRAM. It's on the GPU die itself. It's, as we know from our previous session, it is a per SM resource, and logically, it's a per thread block resource. So it's not a device-wide, it's not a global resource, if you will. And it has a variety of different uses. One of the common uses is for inter-thread communication, and the other common use is to provide for improved performance. Any memory resource that's closer to the processor activity, as we said, is typically faster in the memory hierarchy, and therefore, if we have repeated use of that data, if we move that data to a higher point in the memory hierarchy, in other words, something that's closer to the processor, then we will typically improve the performance of our code. That's not a CUDA unique statement. That's true for most computer architectures. And so shared memory has basically a dual nature. It's commonly used for performance improvement, and it also provides another way to do inter-thread communication within a thread block. As we'll see towards the end, we can use it to improve a global memory access pattern as well. We won't spend much time on that idea in this session, but it's something that you can find blog articles that talk about it, for example. In a common example to demonstrate this is doing a matrix transpose, for example. So I mentioned that shared memory is different. Another way that it's different, besides just being on chip and having different kinds of use cases, is its organization. The way that it's described is to call it typically having 32 banks. Each bank is 4 bytes wide. In my opinion, that doesn't do justice. This organization of shared memory is something that's very commonly difficult for new CUDA programmers to absorb or grasp. And so one of the ways that I like to talk about it is that you can think of it as a two-dimensional array of memory. And the columns correspond to banks. The width of this two-dimensional array in terms of banks is 32. Each bank typically has 4 bytes in it. And so the width of the array in terms of bytes is 128 bytes. And the height of the array is just the amount that would take to use or provide whatever your code is using, or, for example, 48 kbytes if we wanted to talk about the entire shared memory resource. Okay, so 128 bytes wide and as many lines or rows as it takes to make up 48 kbytes is a way to think about shared memory. When you think about it that way, each column of 4 bytes corresponds to a bank. And therefore, in the first row, we have all 32 banks represented, 4 bytes per bank. And in the second row, we have all 32 banks represented. And in the third row, we have all 32 banks represented. So a common misconception is that a bank is nothing more than a location in memory. That's not correct. You can have 2 different locations in shared memory that are in the same bank. Bytes 0 to 3 are in bank 0, and bytes 128, 129, 130, and 131 are also in bank 0 of shared memory. They're in that first column. So this is the way to think about shared memory in terms of organization. And once we have that two-dimensional organization in mind, or those repeating array of banks in mind, then what we need to understand from a performance perspective is that shared memory is capable of delivering one item from each bank in a particular transaction or cycle. Therefore, if I request one item from bank 0 and one item from bank 1 and one item from bank 2 all the way up to bank 31 for a particular load operation from shared memory can service that load operation in the shortest possible time. On the other hand, if I request in the same load transaction, let's say thread 0 wants bytes 0, 1, 2, and 3, and thread 1 wants bytes 128, 129, 130, and 131. It's possible to construct your code that way. And if we continued that, we would call that columnar access, accessing by column instead of by row. If we had a columnar access pattern, then shared memory will serialize those transactions. Shared memory will say, in the first cycle, I'm going to service the first thread. And in the second cycle, I'm going to service the second thread, and so on, for all of the threads that are requesting items from bank 0 in that load operation, in that instruction issued warp-wide. The worst case, of course, is that all 32 threads are accessing the same bank. That we would call that fully columnar access. And in that case, that's the worst possible performance that you can get out of shared memory. And it's 32 times longer than the best possible performance. Now, 32 is a pretty big number. So if I do nothing but access shared memory in columnar mode, then I'm going to have really low performance. Almost guaranteed it's going to be disappointing to use shared memory. On the other hand, if I always access shared memory row-wise, or alternatively, and this is the distinction from DRAM or global memory now, if I simply assure that there is no more than one item per bank across my 32 threads, I will get the fastest possible access. Multiple threads that are accessing the same location, so if thread 0 wants bytes 0, 1, 2, and 3, and thread 1 wants bytes 0, 1, 2, and 3, yes, those two threads are accessing from the same bank, but they're also accessing the same location. This is not a performance issue. This will run as fast as possible. That's what we call multicast. And in modern GPUs, you can have any number of multicast transactions in a single warp instruction that will all be serviced as fast as possible. So here's some patterns of activity. Shared memory can be somewhat, it may be easy to grasp or it may be challenging to grasp. These diagrams may help or they may not. You will probably need to drill into this topic harder if it seems challenging to begin with in order to grasp this fully. But hopefully these diagrams will illustrate some of the cases where we get highest performance and some of the cases where we get reduced performance. Remember, what I'm depicting as bank 0, bank 1, bank 2 does not necessarily mean location, and we'll see what I'll come back to that point in the next diagram. But initially, what we want to start out with is our best performing cases, and in shared memory, we don't refer to coalescing. We talk about something called bank conflicts. The idea behind a bank conflict is simply that two or more threads are requesting items in the same bank, or you could say in the same column of shared memory. However, what we're depicting on this diagram is cases where there are no bank conflicts. So thread 0 is reading bank 0. Doesn't necessarily mean it's location 0. It means it's a location in the first column. Thread 1 is reading bank 1. Again, a location in the second column. Doesn't necessarily mean that that address is adjacent to the one issued by thread 0. It might be, but it doesn't necessarily mean that. Thread 2 is reading bank 2, and so on. In this case, we have no bank conflicts. Each thread is reading from a separate bank, or we could equivalent say writing. It doesn't matter. Bank conflicts and all of the description I've given you so far applies equally to loads and stores from shared memory. So this could be just as equally a write transaction. But as long as the threads are individually writing to separate banks, there is no issue. This is highest performance. This is a non-bank conflicted read or write operation. And likewise, I can have any sort of swizzling pattern amongst the columns in shared memory, amongst the banks in shared memory. And as long as I only have one thread per bank, it's the fastest possible access. That is unbank conflicted. If I have at most across the warp 2 threads reading from a given any bank, as I've depicted on the left side of this diagram, if I have at most 2 threads reading from any bank, we would call that a two-way bank conflict, and it runs half as fast as the cases that we looked at on the previous slide. I could have other levels of bank conflicts. If I have 16 of my threads reading from bank 0 and the other 16 in my warp reading from bank 8, for example, that would be a 16-way bank conflict, and it would run 1/16 as fast as the best case. Okay. Remember I talked about the idea that shared memory can be thought of as a columnar arrangement of memory, a two-dimensional arrangement of memory. Each bank corresponds to a column. Each column corresponds to a bank. And that's more or less what I've depicted on this diagram. So we're thinking now of a shared memory array. We're thinking of it of having a width of 32, and that's exactly our number of banks. So the width of this shared memory array is 32. That's 32 banks. And now we want to ask the question, what happens if the warp accesses a column? Now, we already know what happens if a warp accesses a row. Thread 0 will index into bank 0, thread 1 will index into bank 1, thread 2 will index into bank 2, and so forth. Each thread accesses a separate bank, and therefore it runs as fast as possible. There are no bank conflicts on that transaction, on that load or store operation. But we now want to address the case of what happens if the warp accesses a column. This means that all of the threads are accessing the green column, or all of the threads are accessing the red column, or all of the threads are accessing the black column. In that case, it would be a 32-way bank conflict. That would be columnar access, and it's the slowest possible way to access shared memory. And if you do it extensively in your code, the performance will be disappointing. The question we want to ask, which is our final question for this training session, is there any way that we can improve this? Are there any clever ideas to improve this? There is a clever idea to improve it, and the clever idea is to use padding. The idea here, remember, shared memory is typically defined by the user, and if we're doing what's called a static allocation of shared memory, we're basically defining an array, and we're in the subscript definition of the array, we're passing the dimensions of our two-dimensional array. The first subscript would correspond to the number of rows, and the second subscript would correspond to the number of columns. I'm talking about the logical size of the array, not the physical arrangement of the shared memory. The physical arrangement of the shared memory doesn't change. It has 32 columns or 32 banks. But what we want to do now is pad our array so that it has 33 columns. So if I had a shared memory array and the first dimension was 32, now instead of the second dimension being 32, we're going to make it 33 columns. These are logical columns now. The effect of this is that it will stagger or scatter our bank arrangement. Again, there's nothing changing physically underlying, but what we're talking about is a relationship between the logical arrangement of data in my logical array and the physical arrangement of the storage locations in shared memory. And so by changing the number of columns from 32 to 33 without changing my access pattern, in other words, when I access this shared memory, I never access column 33. I never have an index in the second subscript of 32. My indices for the first and second subscripts when I'm accessing it always still remain in the range of 0 to 31. But in that case, if I access in a columnar fashion, what we see now is if we look down the first column here, we have an arrangement of banks which are not all the same bank. Down the first column, we see an arrangement where bank 0 appears in the first location, bank 1 appears in the second location, and so on. And so I can access, with this additional padding, I can do columnar access into my logical array without running into my bank conflicted scenario. Why is this important? Because there are situations where we want to be able to conveniently access data in both a row and columnar way. There's plenty of algorithms that sometimes want me to access data row-wise and later want me to access data column-wise. A trivial example of this is a matrix transpose operation. And if you'd like to have a detailed treatment of this topic, I suggest you Google CUDA matrix transpose blog, and you'll quickly find a blog article that dives into this topic in detail. And in fact, I may have included it in my notes at the end of this session. So that's a clever trick which is commonly used to allow shared memory to provide for both row or columnar access to an array at basically full speed. So in summary then, what we've learned is that global memory has a access pattern that likes coalescing. And in order to maximize the throughput with global memory, we want to use patterns, in other words, arrangement of addresses across my warp, such that those addresses tend to be grouped together, adjacent and contiguous in memory. And when I do that, I tend to observe nicely coalesced accesses and tend to get to maximum throughput from global memory. We know from our previous session that if we have a small piece of that data that we want to operate on, let's say per thread block, we can use shared memory as effectively a user-managed cache for that small chunk of data, that tile of data, if you will. And we might then want to use shared memory in that case. And when we use shared memory, we want to pay attention to something called bank conflicts, which are in some ways similar but not exactly the same as the concept of coalescing. Shared memory actually is a little bit more flexible than global memory when it comes to being able to do scattered accesses. And finally, for all of these topics that we've discovered last time and this time, you'll take your cut at it as a programmer, and then you'll use analysis-driven optimization to figure out if you've done a good job, and if not, where things are going awry. So with that, I'm at the end of the training for this session. We do have some future sessions coming up. I want to once again point out the homework. The homework is covered on the next slide. And the reason that I'm choosing to mention the homework here is I just want to briefly describe it. Namely, the homework will walk you through a very simple coding exercise that asks you to create a set of row sums and a set of column sums out of a two-dimensional matrix. And you'll be asked, so you'll write a CUDA kernel for each. And you'll be asked to analyze the performance of those two CUDA kernels. And what you'll observe is that the performance is not the same when I'm doing row sums or column sums for what I would call a straightforward realization, which is what you're asked to do in the homework. One of those two will be a more troublesome case. And we don't actually answer the question how to address the troublesome case in this session. That will be our next session. So when we get to atomics, reductions, and warp shuffle, we'll begin to unpack the process of coding strategies that you can use to address that more troublesome case of the two examples that are presented. A row sum you can think of possibly as row or columnar access into a memory array, and the column sum is just the other. If you call one row access, the other one will be columnar access, or vice versa. And so we know for shared memory without our special trick, but we certainly know that it's true for global memory that adjacent or row-wise access across a warp is the most efficient pattern. And columnar access in global memory is just inefficient. There's no way around it. Okay? That will immediately drop you into the worst case efficiency, and you'll be exciting one of those two in one of the two kernels that you write. When we get to our next section on atomic reductions and warp shuffles, we'll start to unpack the process of fixing one of those cases in global memory. And we have several other sessions that hopefully you will join us for in the future. So the homework is available to you. Sorry, I'll go to the homework slide. The homework is available to you now, and in a few minutes, I'm going to turn this over to Robbie, and those who are wanting to can stay online and work through the homework with Robbie. Here's some suggestions for future study. And with that, we're at the end of this session. So before I turn it over to Robbie, what I would like to do is pull up the chat. Let me do that now and see if there are any questions that I can answer. Is the global memory throughput dependent on the device alone or also the machine bus, say PCI versus NVLink? Global memory throughput is dependent only on the device. Global memory does not normally, I need to back up a little bit. So global, as we've said, is a logical space. And typically, when we refer to global memory, we've been referring to data that would be, let's say, the transfer data done in a CUDA memcopy operation, or the allocation done using CUDA malloc. When we use global memory to refer to those types of things, that data is present in the DRAM memory. And so when I do a CUDA malloc operation, I'm carving out a space in the DRAM memory, and when I do a CUDA memcopy using that pointer that was returned by CUDA malloc, I'm copying data to or from that allocated space in DRAM memory. Once I then begin to write code that executes and uses that data in that particular area of global memory, that is issuing, to retrieve and store the data, it's issuing transactions directly to the DRAM, and those transactions don't flow over the PCIe or NVLink bus. Now, if we expand our view a little bit, global memory, as I said, is a logical space. It turns out, although we haven't talked about it so far in our study of CUDA programming, it turns out that it's possible to map system memory into the logical global space of the GPU. In other words, without transferring data to the GPU can issue transactions that will go across that system bus and will retrieve or store data directly from the host. We're going to cover that later in one of our subsequent sessions when we get into concurrency. We'll talk about something called pinned memory, and there are other related topics as well. But pinned memory is one example of a way that I can carve out a section of host memory and make it directly available to the GPU without transferring it to the GPU device memory. That memory allocated that way out of the host also lives in the logical global space. And when I write CUDA code, the code doesn't look any different. There's a pointer to that data, whether that data is physically resident in DRAM memory, in other words, the GPU's DRAM memory, or physically resident in the host memory. And if it happens to be a pointer to pin memory in the host, then when the GPU code accesses it, it will actually issue transactions across the host-to-device bus. In that case, that bus will become the bottleneck or the predictor of performance for that transaction. But in most of our discussion here today, we've been more or less equating global memory with the data that is stored, in other words, physically backed in the DRAM associated with the GPU itself. That's the typical CUDA usage. It's everything that we've covered in this first 4 sessions of this series, but it's not the only possibility. The next question is, where does unified memory fall in the picture? We're going to have a training session in the future that specifically deals with unified memory, so I'd like to defer that question mostly to that training session. However, unified memory in its most optimal realization doesn't have a single physical location. It's actually memory that migrates. The data migrates. And so unified memory is a logical allocation that at a certain point in time can live, in other words, be physically backed by GPU DRAM, and at other points in time it may be physically backed by CPU memory or host memory. And in order to understand that in more detail, I'd like to refer you to our training session in the future where we will deal with unified memory. Global memory is GPU global DRAM, not host DRAM. So I've tried to clarify that a little bit. I agree with that statement insofar as we've gone in this training session. Up till now, we've been more or less equating global memory with GPU DRAM. There's a distinction here between the physical backing and the logical space. And the logical global space for a GPU is actually bigger or has other possibilities besides just data that's stored in physically backed DRAM, in other words, GPU DRAM. It also has the possibility to refer to data in the logical global space that is physically backed by system memory, and we will cover that in a future topic. So there is no cache coherence protocols between different SMs, not for the L1, that's correct. The L1s are not cache coherent, period. The L2 is a device-wide resource. Therefore, with respect to a single GPU, it is by definition coherent. There is only one L2. Max is probably, I hope, repeating some of the things that I said already, and hopefully his description in the chat is equivalent to what I gave you verbally. Okay, so with that, I think I've reached the end of the chat, and I would like to open it up briefly for spoken questions. I don't know if we're going to have any of those. If we're not, Tom, if we only want to field them by chat, then I'm ready to turn it over to Robbie.
No, if people have open questions they'd like to ask verbally, they can go for it. We'll give them a minute. Or perhaps if there are questions, you could just ask them in chat, I guess. Sounds like a quiet crowd, so to speak, today. So I guess with that, before handing it off to Robbie, I'd just like to say thanks again.
There is one more question that just popped up in the chat.
Oh, yep, there we go.
If we use too few blocks, meaning we split our data into large chunks, would that cause cache thrashing for that particular SM? Yes, it could. The L1 and L2 caches should be thought of at a high level to be similar to other types of caches that you may be familiar with. If the working set that your code is operating on, we could think of that globally for across your entire kernel with respect to the L2, or we could think of that with respect to a single thread block and the L1, either case. But if the working set for your code for a single thread block in the L1, or for your global device and the L2, your kernel and the L2, if the working set for your code is larger than the footprint of the cache, so a typical L1 cache footprint might be in the order of 16 to 128K bytes, depending on which GPU we're talking about exactly and the configuration of that GPU, but that's roughly the range, 16K to 128K. If your working set, let's say per thread block, is bigger than that, then you run into the possibility of thrashing. That was the word used. And the idea behind thrashing is the cache becomes inefficient because I'm repeatedly asking the cache to access data that it doesn't currently have stored. And the reason for that, without going into a long example, is just that my working set, my overall data set size, is bigger than the cache footprint. We could state almost exactly the same thing for the L2. Across my kernel, if my working data set is larger than the L2 cache, then the possibility for thrashing occurs. And the L2 cache is a device-wide resource in the Tesla V100 family, which is our most powerful GPU currently. That is a 6 megabyte cache. Still not huge by CPU standards, but it's a lot bigger than the L1 cache. If so, what should be the largest chunk of data that we should send to each SM? Hopefully I've tried to cover that. When you start to think about this idea of how much data do I want to process with this group of threads or in this kernel, with an eye towards the cache, then we call that an optimization for cache, or sometimes we'll refer to that as a cache blocking strategy. And what I may want to do in cache blocking, for example, is process my data a chunk at a time so that I can take advantage of reuse in the cache. And hopefully I've given you some guidance there. The L1 cache is so small that I would suggest it's really not appropriate, or at least at this level of instruction, I would not encourage you to think about cache blocking strategies. One of the primary purposes for the L1 cache is to do what I described a few slides ago, and that is to stitch together that access pattern which commonly occurs when one warp is accessing data that straddles lines or segments. The L1 cache will fix that for you. It can fix that pattern even with a very small size like 16K bytes. It can fix that pattern for you with enough locality, temporal locality of access. In other words, if the warps that are adjacent to each other are making the requests close enough to each other in time, then it's likely that the L1 cache will fix that problem for you. That's, I would argue, the primary purpose of the L1. You don't have to do anything to achieve that. It just does that for you, and you should just, acknowledge the fact that the L1 is providing you a benefit that you can't measure. If you want to get into cache blocking, I would suggest the first strategy for cache blocking might be to think about the L2 because it's larger, and then perhaps think about the L1. And when you think about the L1, you'll have to do that on a thread block by thread block basis. Is max function used inside kernel is thread divergent? I don't know what that means. If I have a max function that's running in a single thread, by definition, it's not divergent. I don't really know what that means. Also, do loops cause thread divergence? A loop can cause thread divergence if the loop termination condition varies across the threads. Okay, the loop progress or termination condition, depending on what kind of loop you're talking about. So if I have a Boolean test to terminate a loop, and that Boolean test varies in behavior across the threads in the warp, then the existence of that for loop or while loop or something like that can definitely cause thread divergence. Yes. Okay, reached the end now of what I think are the comments in the chat, so I would like to turn it over to Robbie at this point.
I just want to, this is Helen from NERSC, just want to remind NERSC users we have a reservation. So if you want to follow Robbie's demo, you can do so. You just use the NERSC specific commands to ask for nodes. I assume Robbie will use Summit instead of Core GPU for the demo.
Okay, while Robbie goes ahead and gets set up, I just wanted to say thanks once again. We appreciate you guys at NVIDIA, talking specifically to Bob at the moment, for putting this on for us, putting together these presentations. So we appreciate it, and we'll see you next month, Bob.
If you do leave now, please remember to do some survey for us. We do appreciate your feedback.
Yep, under the survey tab on the event page, you can fill that out. And you might as well do it now, otherwise I'll just send out emails asking you to do it later. Thanks.
Can everyone hear me?
I can hear you.
Sounds good. Let me share my screen. Oh, one sec. I don't normally use Zoom, so I have to give it permissions. I have to restart Zoom and join in order to share my screen. Give me one sec. Okay, let me try this again. There we go. Can everyone see my screen?
Yep, I can see it.
Excellent. All right. So for this exercise, we're going to, so Bob talked a lot about memory coalescence, and I'm sure some of you are wondering, how can we observe what our memory access patterns actually look like when we're executing our code? So that's what we're going to go through today. So the first task in this lab is to create a simple matrix row and column sum application in CUDA. The skeleton is given to you in the matrixsums.cu file. I am going to actually skip that and just use the solutions file for now, because I want to focus on how to use Nsight Compute and how to analyze our runtimes. The matrix sum is actually somewhat similar to the matrix multiplication that we did in the first homework. So this should be a relatively easy exercise for you guys to complete. To that end, I've obtained an interactive job on Summit. So if you're running on Summit, I'm sure you recognize this portion of the instructions from previous labs. So what I've done in order to obtain an interactive session rather than to submit each one of my job runs interactively is I've done just my vsub portion of this command with a bigger wall time, and instead of interactively doing a JS run command, I interactively do /bin/bash. So in case you're wondering how to get an interactive node, that's how you do it. And then we can get started. So first thing I want to do is load CUDA and compile our code. All right. And in order to run our code to make sure that it compiled correctly, I will just do my JS run command /matrixsums. And it says that I have row sums are correct and column sums are correct. All right, good. So next we want to load Nsight Compute. So this is one of our profiling tools. We are going to use this. First, we're going to time the kernel executions and get a basic overview of what's going on in both our row sum and column sum kernels. And then afterward, we're going to query some specific metrics to see what's going on related to our memory accesses. So you actually don't have to type the specific version on Summit. So I can just module load Nsight Compute. Okay. And then I will run our matrix sums application. Cool. All right, so this spits out a bunch of information for us, but what we can see is the way that the output of Nsight Compute is structured is you have a kernel. So in here we have our row sums kernel, and then it gives us a bunch of information about that kernel. And if we scroll down, our column sums kernel and a bunch of information about that kernel. If we had other kernels, it would do the same thing for each kernel. We see our duration here in milliseconds. So for our row sum, we're getting 3.31 milliseconds, and for our column sum, we are getting 1.37, so about 3 times faster. And then it gives us some other.
Hey, Robbie, this is Tom. I don't know if it's my screen lagging or if we just can't see anything other than your browser window. I'm still seeing your browser window.
Oh, really? Okay, that's not good.
So I don't know if you just need to share your whole screen instead of just a portion, or if my screen is lagging. Can anyone else confirm that?
I thought I shared my whole desktop.
Except we can only see the black screen right now. Oh, yeah, it's working.
There, I see your screen.
Huh. I wonder if I am connected to VPN. I wonder if it's that. You see my terminal now?
Yes.
Yes.
Thanks.
Okay, I'm not sure why that was so laggy. All right, so can you see this row sum that I just highlighted?
Yeah.
Okay, all right, cool. So like I was saying, Nsight Compute organizes the output by kernel. So we have our row sums kernel up here, bunch of information, and then our column sums kernel. As I mentioned, within each kernel, there is a duration field, which will tell us the whole runtime of that kernel. Our row sum was giving us 3.31 seconds, and our column sum is running a little bit faster at 1.37 seconds. So if we want to see why that is, hint, hint, it involves memory accesses. So we can go back in here and query some specific metrics. So we want to measure our global load efficiency, like Bob was talking about in the lecture portion. So we're asking for two metrics. We're asking for the number of global memory load requests and the number of sectors requested for global loads. So the first metric is going to be basically our denominator, which is the number of requests. And we want to get the number of transactions per request that actually happen. Obviously, lower is better. So by dividing the second metric by the first metric, we would get that number. So if I go ahead and run our application again, querying these specific metrics, cool. Okay, so again, it's organized by kernel. So we see our row sums kernel is actually doing a lot more memory transactions per request. If we divide these two numbers, we'll get 32 transactions per request for our row sums kernel, and we will get 4 transactions per request for our column sum kernel. So that's indicating that by default, our column sums kernel has better memory coalescence than our row sums kernel. And like Bob said, we will talk next time about how to actually optimize our row sums kernel using shared memory to improve that. I just wanted to give you guys a quick overview of what Nsight Compute looks like and how you can query specific metrics to get an idea of what's going on in your code. And I put a blog article down here that has a very similar example. And if you want to read ahead, it talks about how to actually optimize using shared memory in there as well. And it also gives us a compare and contrast between our old tool. So if anyone is familiar with NVProf, there was a way to query the global load efficiency in NVProf, and then this is how you would do it in Nsight Compute. Nsight Compute gives you a lot finer granularity of what you're able to query in your application. So does anyone have any questions about that? This is a pretty short lab.